Oh, Rebecca.
Um, I emailed you like a few minutes ago, but my question is for the midterm two, if we went to the post midterm review for midterm one, are we still gonna like get the extra credit or?
Yeah, I added the 5% credit to your midterm one score for the students that attended the post midterm one review. Although it doesn't reflect it on Gradescope, but it reflects it in my grade spreadsheet.
Okay, thank you.
Mm-hmm. And also, when I was asking the class to send me private messages during the lecture, I realized I was getting them at two different accounts. Well, because I'm on here with two different devices right now. So maybe just so it's easier for me, you can send the private messages to this one and not to my other device, which I use to share the screen on my Surface laptop. Okay, so I think I'm going to start off by finishing up one last question that I had from the end of lecture yesterday. So let me show you what I mean. Okay, so this is the last thing that I said at the end of lecture yesterday. I said what the general rules for transforming graphs of sine and cosine are. If you start with a basic sine graph, but then you put a factor in front, well, that will make it correspondingly taller or shorter by a factor of a. That will change the amplitude. If you multiply by a factor inside, that will compress it horizontally or change the frequency, as we would say in physics. You also have a horizontal shift term. And you can have a vertical shift term. So here, I'm just rewriting the same thing I just wrote above. So similarly, the same rules apply for cosine. A times cos of b times x minus h plus k has amplitude a, period 2 pi over b, midline y equals k. So why don't we just warm up this morning by answering this example that I asked you, or that I have written here. So can you private message me? What is the period, the amplitude, and the midline of this sinusoidal graph, 10 cosine pi x minus 17? So send me both or all three of the period, amplitude, and midline. I know it's early to start having to write stuff. Tell me about it. All right, you folks are doing pretty good. Cool. Okay, most people are getting this. So I'm now going to use the period, amplitude, and midline to help myself draw a graph of this function, a rough sketch. So here's the graph of 10 cos pi x minus 17. And I apologize for the lousy artwork here, but hopefully it contains the important features. The midline, let's use that first. That's down at negative 17. Horizontal line down at y equals negative 17. Amplitude is 10, as you correctly said. So it's going to go up 10 and down 10 from negative 17. That means it's going to go up as high as negative 7 and down as low as negative 27. The period, most people correctly said, was 2. So this graph's going to repeat every 2. So this is not going to be to scale, but let's say here's 2 and 4, negative 2, negative 4. So let's see, cosine always starts up at a peak, and then it's going to go down to a valley and back up to a peak in a space of 2. And there, I've got one period of the graph. Similarly, we'll do that periodically. And such. So there's a graph of that function. Cool. Okay, that's just what I wanted to finish off from last lecture. Any questions? Okay, so that wraps up this section. The next section is a section that we are going to skip because we don't have time to do it. But because it's kind of important, it's kind of useful, it's just not as important as the other sections, I at least wanted to point out the main features of section 6.2, which are graphs of the other 4 trig functions. Because so far we've only done sine and cosine, but you could graph tangent, cotangent, secant, cosecant, etc. So I'll just, how about show you like what a picture of those graphs looks like. And definitely the most important one is tangent. Of the remaining 4, the most important graph is tangent. So let me point out some features of the graph of tangent, which you can see here displayed on the screen. The graph of tangent has vertical asymptotes. The first one occurs at pi over 2. Then it has another one at 3 pi over 2. And it keeps repeating every pi. It has a negative vertical asymptote at negative 3 pi, or sorry, at negative pi over 2. And interestingly, the period of tangent is only pi, not 2 pi. Right? Almost all the trig functions have a period of 2 pi, except tangent, which due to how it's defined and like some canceling of negative signs, the period ends up just being pi. So we're going to use that graph a little bit in today's lecture, actually. And I'll just show you like what the other trig graphs look like. For example, here's secant, which is 1 over cosine. And here's cosecant. Looks a lot like secant. And here's cotangent, which looks a lot like the graph of tangent. And you know what? I don't think I have ever used the graph of cotangent for anything in my life. So this one's probably not going to come up very much, which is why we're skipping this section. Okay, so that was a lightning quick rendition of section 6.2. Any questions? Okay, then we will go on to the main topic of today's lecture, which is inverse trig functions. So you might have noticed that this is a theme in this class. We introduce a function and then we introduce its inverse, right? That's what we did with exponentials. First, we introduced exponentials, and then we introduced logs, which were their inverses. So now that we've introduced trig functions, let's do their inverses. And before I do that, let me remind you what the inverse of a function is. So by definition, if f of a is equal to b, then f inverse of b is equal to a. If there's one caveat, the function is one-to-one. If it's not one-to-one, then the inverse is not well defined. We don't know, like what value should the inverse take? There could be multiple possible such values. So that's the definition of the inverse for any function, any one-to-one function. Now let's talk about sine. Let's look at the graph of sine, which, thanks to modern technology, I can get a graph of. Okay, so there's a graph of sine of x, and we can see right away that it is definitely not one-to-one. This would fail the horizontal line test badly. If I drew a horizontal line, it would have many points of intersection. So sine is not one-to-one. Maybe you remember there was something that we could do when functions weren't one-to-one in order to get an inverse. Valentina?
You can restrict its domain.
We can restrict the domain, so that's exactly what we're going to do. So next the question is, well, what should we restrict the domain to? And in a sense, this is kind of arbitrary, but it also is kind of the most obvious and useful choice. So if you look closely at the graph of sine, let's see, it repeats every 2 pi. Here's pi. Here's pi over 2. There's negative pi over 2. Let's restrict it to lie between negative pi over 2 to positive pi over 2. In that case, the graph is just that green part. So I can like erase the rest of it. Okay, and now it's 1 to 1, right? That little piece that you see remaining would pass the horizontal line test. So this is now 1 to 1, and this is how we're going to define sine inverse. So here is the definition. If x is between negative pi over 2 and positive pi over 2, then sine of x equals y means sine inverse of y is equal to x. And there's your inverse sine function. I.e., or in other words, there's another name for the sine function, by the way. For some reason, this is for historical reasons, we also call the sine function, sorry, we also call the inverse sine function the arc sine function. So, oops, also known as arc sine of y is equal to x. So sine inverse of some ratio and arc sine of some ratio mean the exact same thing. It's just two different notations for the exact same thing. They're both the inverse sine function. And note that this is not 1 over sine of t. Okay, so don't ever make that mistake. I know the notation is a little bit wonky because when we put a 2 up there, that did mean sine squared, but here it's a -1 power, but it does not mean 1 over sine. It means inverse sine. So let's practice with an example. How about the sine inverse of 1/2? What's the sine inverse of 1/2? It's the angle whose sine is 1/2. What's the angle whose sine is 1/2? Anyone know? Rebecca?
30?
30, yes, good, correct. Or I'll put it in radians since that's the default output. But yes, 30 degrees or pi over 6 radians. Why is that? That's because sine of pi over 6 is equal to 1/2, and pi over 6 is in the interval of -pi over 2 to pi over 2. So notice that the inverse sine function, the output is an angle, okay? That if you can just remember that the output is an angle, that'll help you sort of remember what you're supposed to calculate. You input a ratio and you get out an angle, as opposed to the sine function where it's the reverse, right? With the sine function, you take the sine of an angle and you get a ratio. For this inverse sine function, you take the inverse sine of a ratio and you get an angle. So wait, actually, I just did this example. Here, forget this example. I'm going to change this. Now, here's another example. So, sine of 2 pi over 3 is, what is that? Is root 3 over 2. Yes or no? Sine inverse of root 3 over 2 equals 2 pi over 3. Jose says it feels like a trick. Yeah, he knows I like to try to trick you with these questions. So could this be a trick? Well, it looks like that's what the definition of the inverse is, right? Except there's that one domain rule. So sine inverse will only ever spit out a number that's between negative pi over 2 and positive pi over 2. So most people said the answer is yes, but is this within that permitted range of the inverse sine function? No, it's not. This could not be the output of sine. So the answer is no. Because 2 pi over 3 is not in the interval negative pi over 2 to pi over 2. Yeah, so that could not be what inverse sine of root 3 over 2 is. In fact, what is inverse sine of root 3 over 2? I just told you it's not 2 pi over 3. It's going to be the angle that's in our permitted interval. Ah, okay. Some people are private texting me the answer, and they are correct. This is pi over 3. Yeah, so pi over 3 is indeed inside negative pi over 2 to pi over 2. And sine pi over 3 does equal root 3 over 2. Okay, so yeah, I was able to trick you all there because it was almost correct. It just didn't satisfy the domain rule. So that domain rule is tricky. So as someone who's taught calculus many times, I know that this is one of the things that a lot of students get hung up on. And if you can get this feature of the inverse sine functions down now, it will help you a lot in calculus. In 20A and in calculus 1 and especially calculus 2. So Any questions now that we've done sine inverse?
I have a question.
Uh-huh.
So on the graph you did of sine, of the inverse sine, shouldn't like the inverse of the graph be like tilted where the x and the y change?
Yeah. Oh, okay. So you're asking about the graph. Good question. Okay, yeah, I like that. Let's try and draw the graph. The graph of sine inverse is kind of weird, but it's what I would get if I flipped this around the line y equals x. Let me see if I can draw it by hand. I probably shouldn't try to do this, but I think it'll be something like that. But let's check here. So yeah, that's a very good question. Let's look at the graph of sine inverse. I tried to draw it there, but how about we use Desmos? And there's your arcsine graph, which is the same as sine inverse. And in fact, you can even compare them to the graph of sine as well. It would probably be better to compare it to the graph of sine on a restricted interval, but I don't remember the notation for that in Desmos. So here, let's just use this graph. Let's see, was I kind of close? Kind of. Yeah. Cool. Any other questions? If I wanted to put points on the graph of sine inverse, that's like a good exercise. So you can only take the sine inverse of a number between 1 and -1, and you will only get an angle as large as pi over 2 and as small as -pi over 2. Okay, so I guess now I'll do cosine. I'm defining sine inverse, cosine inverse, and tangent inverse in this lecture, and this is kind of technical, so I apologize if this part, if this lecture is kind of boring. It's just we have to do it. So I'm now going to do something very similar for cosine. Let's start off by looking at a graph of cosine. And as before, we're going to restrict the domain. So there's a graph of cosine, and we need to restrict the domain in such a way that it's 1 to 1. So the way that this is done, which is the standard, the default way, is to restrict the graph to lie between 0 and pi. So we're only going to look at x between 0 and pi, and you can ignore the rest of the graph for the purposes of the inverse cosine. So here's the definition. If 0 is less than x is less than pi, and cosine of x is equal to y, then cos inverse of y is equal to x. Or we also have the arc cosine notation, which means the exact same thing. So let's practice with that. And as before, once again, note cosine inverse is not 1 over cosine. Okay, so how about arc cosine of one over the square root of 2? Since cosine of pi over 4 equals 1 over square root of 2, and pi over 4 is inside that interval of 0 to pi, arc cos of 1 over root 2 is equal to pi over 4. Okay, so how about you all do this example and private message me, what is cosine inverse of negative root 2 over 2? And let's get everyone to respond, please. In fact, if it helps, I'll even show you a unit circle. Where's my unit circle? Okay, so let's do it. Now, looking at the unit circle, if you thought that negative pi over 4 was an answer, that's understandable because that has the right, sorry. No, it doesn't. I take that back. Forget what I was just saying. Okay, so to find cosine negative, I was going to talk about negative pi over 4, but that has a cosine of positive root 2 over 2. So there's obviously many different angles whose cosine is negative root 2 over 2. This angle, 3 pi over 4, has its cosine equaling negative root 2 over 2. This angle, which is 5 pi over 4, has its cosine being negative root 2 over 2. This angle, which is negative 3 pi over 4, has its cosine being negative root 2 over 2. And I could go on. Only one of those is inside 0 to pi. And that's the one that's going to be the cosine inverse, and that is the 3 pi over 4 angle. So since cosine of 3 pi over 4 is equal to negative root 2 over 2, and 3 pi over 4 is inside 0 to pi, cosine inverse of negative root 2 over 2 is 3 pi over 4. Okay, any questions? Whew, okay, one more inverse function to define, and that's inverse tangent, aka arctangent. So let's look at the graph of tangent, and now you're going to see why I bothered to show you that graph of tan that I showed you at the beginning of lecture today, because we're going to use it right here. So there's the inverse tan. And as I mentioned, it has vertical asymptotes at pi over 2, at negative pi over 2, and a whole bunch more, but we're going to restrict the domain to just lie between negative pi over 2 and pi over 2. And because of the asymptote, it's not actually defined at plus or minus pi over 2. So actually, the domain can't even include the endpoints, which is why here's the definition. If x is strictly between negative pi over 2 and positive pi over 2, and tan x equals y, then tan inverse of y is equal to x, i.e. arctan of y is equal to x. So again, we can't include the endpoints of the interval at pi over 2 and negative pi over 2 because tangent is undefined at those points. So here's an example. Since the tangent of pi over 4 is equal to 1 and pi over 4 is inside negative pi over 2 to positive pi over 2, tan inverse of 1 is equal to pi over 4. So how about you all try to find arctan of negative 1. So private message me, what's arctan of negative 1? Everyone do this one, please. And while you're doing that, I'm going to go collect some graphs. So keep on doing that if you haven't messaged me yet. Okay, let's see. How did you folks do? All right. Half of you are getting it right. Let's see. So arctan of negative 1 is the angle whose tangent is negative 1, but specifically the angle between negative pi over 2 and pi over 2. So your answer must lie inside the open interval negative pi over 2 to positive pi over 2. Since tan of negative pi over 2 is negative 1 and negative pi over 4 is inside that interval, arctan of negative 1 equals negative pi over 4. Okay. Any questions? Whew. So what you see below you now is the graphs of some of these inverse functions. Like on the left, that's y equals cos inverse of x. Then in the middle, that's y equals tan inverse of x. And then on the right, that's y equals sine inverse of x. And you don't use the inverse graphs very often, but occasionally. Probably the tan inverse graph is the one that is most commonly used. It's kind of interesting, actually, because it has two horizontal asymptotes. One is at positive pi over 2, and another one is at negative pi over 2. And the tan inverse function ends up being the solution to some difficult integration problems, which you're going to learn about, well, once you learn what the heck an integral is, which will be in 10b, Math 10b. Valentina?
I'm kind of confused. How do you get that tan, the inverse tan answer?
So, okay, I needed an angle whose tangent was -1, because, so tangent, let's check, what's tangent of negative pi over 4? That's sine of negative pi over 4 over cosine of negative pi over 4. That's -1 over root 2 over +1 over root 2, which is -1. But we also need to make sure that the angle lies between negative pi over 2 to pi over 2. Right, that's because we had to restrict the domain. Here, like, let me go back up to this graph. So once we restrict the domain, that means you can erase all these other ones for the purposes of determining tan inverse. You can ignore everything except the part that's between negative pi over 2 and pi over 2. So the angle whose tan is, see, -1, there's -1. This angle right here is negative pi over 4. So tan inverse of -1 is negative pi over 4. Good question.
So to get the answer, we would have to look at a graph for the circle.
I hope you do. Yeah, I strongly recommend looking at graphs. I think I might have mentioned that like last week, but yeah, always look at the graph. It's super helpful. In fact, what we're going to talk about in solving trig equations, oh, it's so much easier. It gives so much more intuition if you look at the graph. So yes, I highly recommend you get in the habit of looking at the graph. And what we just saw was, if we looked instead at the graph of inverse tangent, let's see, -1 is right there. So apparently this must be negative pi over 4. That is to say, this is the point -1, negative pi over 4. Whew, okay, yeah, this is getting pretty technical, folks. So again, I can't tell you how many students I've encountered in calculus who had trouble with this, struggle with this. So there's a very good reason that we're showing it to you. It's technical, it's tricky, but you will have to use it. So it's like a necessary evil that you have to suffer. But it allows us to do some cool things that we formerly were unable to do. Like, for example, we can find all these different angles that formerly we could not. Okay, so in these examples that I've been doing, like arctan of -1, you were able to do it without a calculator because because that ended up corresponding to a point on the unit circle that corresponded to one of the special right triangles. Most angles, though, you can't do by hand, right? Unless, where's my unit circle? So unless you're looking at one of the angles that's on the unit circle here, you have to use a calculator for most calculations. One of your challenges is going to be to have enough experience to know the difference between an angle that you can do by hand versus one that you have to evaluate using a calculator. So the 3, 4, 5 triangle, it does not correspond to any point on the unit circle. So in order to do this next example, which is to find the angles in a 3, 4, 5 triangle, we're going to have to use a calculator. So here's a 3, 4, 5 triangle, and let's give a name to, how about this angle, and call it theta. And up until this point in the class, we did not have a way to figure out what theta was. We did not have the tools to do it. But now that we've learned about the inverse trig functions, you can actually tell me what theta is, like in degrees, at least to maybe the nearest decimal or nearest hundredth place or so. So how about let's do that? In fact, here, I'll do this one. So first, I have a choice. There's many ways I could answer. I could use sine or cos or tan. I think I'll use sine because the sine of theta apparently is 4/5. Okay, so let me get maybe a quick yes or no. Theta is sine inverse of 4/5. Okay. Everyone's saying yes, no one's saying no, and you are correct. Yes, because it's clearly an acute angle. It's between 0 and 90, so it's within the range of sine inverse. And, well, that's what it is. Now, we can't do this by hand, but we can get it from a calculator. So how about I punch it in on a calculator? I realized earlier in the lecture today, at one point, I was doing something on Desmos, and I forgot I wasn't sharing that part of my screen. So let me share my whole screen so you can see that. Okay, so let's go to the scientific calculator function of Desmos. Oh, and a quick note about scientific calculators. You know, when we were taking the midterm, I said in the instructions on the midterm that scientific calculators were permitted, including online ones. So this is what I meant. I realized afterward, maybe not everyone knew what exactly a scientific calculator is. This is an example of a scientific calculator. Notice it doesn't do any graphs for you. It doesn't solve equations for you or show steps for a solution. That would be cheating. So like don't use ones that will show you the solution to an equation and the steps to solve it. No. Just a basic scientific calculator such as the one at desmos.com/scientific. Okay, keyword there is scientific. So this would be permitted. And if I just plug in, let's see, sine inverse of 4/5, I get 53.13. Notice I'm in degrees mode. Okay, if I wanted it in radians, it would be 0.927, but I'll leave it in degrees mode. So about 53 degrees. Let's round it to 53 degrees. So this is approximately 53 degrees. Can someone think of another way that I could have found what theta is? Like I didn't have to use sine inverse. You have actually some choices here. What's another function I could have used to get what theta is? Oh, cosine inverse, someone says. Okay, I like that. Cosine inverse of what? What would I take the cosine inverse of? 3/5. Good. Cos inverse of 3/5 should give me the same answer. In fact, let's just check. See if I did it right. So if instead I did cos inverse of 3/5, oh good. I also get the same angle, 53 degrees approximately. So yeah, it's up to you, whatever way you like. So, okay, theta is about 53 degrees. Let's get the other angle. How about I call it phi? Can someone tell me what is phi? Or maybe approximately what is phi? It's not that hard now that we know what theta is, approximately.
37 degrees.
37, good, yeah. Phi is the complement of theta. So some of you have been working with complements on the homework, I know. How do you take the complement? You do 90 minus the other angle, i.e. phi is 90 degrees minus whatever theta is in degrees. So that's 90 degrees minus, well, approximately 90 minus 53 degrees, which is 37. So phi is approximately 37 degrees. Wow, okay. So we can now solve for the angles of a 3, 4, 5 triangle. This is pretty cool. We're expanding our mathematical repertoire or toolkit. And you can imagine, like, there's all sorts of situations where it would be useful to figure out what an angle is. By the way, this example that I just did is much like one of your homework problems on the latest homework assignment. So in that problem, I asked you to come up with your own Pythagorean triple, not 3, 4, 5, and not any multiple of 3, 4, 5 either, okay? So like, a 6, what is it, a 6, 8, 10, that's just twice, that's just a 3, 4, 5 triangle that has been blown up to twice its size, but it will have all the same angles because it's similar. So you have to come up with a totally new Pythagorean triple. I asked you to not use a 3, 4, 5, and don't use a 5, 12, 13 either, because those are both Pythagorean triples that I've already talked about in class. And I kind of want you to, you know, do some research, do some discovery, and find your own Pythagorean triple. They're out there. There's actually an infinite number of them out there. In fact, there's a really cool, oh, maybe I should show you. Okay, I wasn't planning on talking about this, but just because I'm on the topic, one of my favorite YouTube channels is 3 Blue 1 Brown. I don't know if any of you have heard of this YouTuber, but he does math videos that are really interesting. And he used to like work for Khan Academy for years. He made videos for Khan Academy. He went to Stanford. I met him actually. The guy's name is Grant Sanderson, and he came and spoke at UCSD about a year ago, and I went and talked to him. And he makes these videos where he employs animation to convey various mathematical topics. And what's really cool is that he can show topics using animation that up till now, using modern technology, it was not possible to do. So you can see animations that convey ideas that really could only be done in the modern age using modern technology. And it's so neat to see like the animation that gives you a physical idea of topics that formerly had to be imagined in your head. And he's got a video called All Possible Pythagorean Triples Visualized. And it uses some concepts that you folks have not learned about yet, like complex numbers, but nevertheless, his videos are made to be digestible by a general public audience. So I think you could probably appreciate it and understand most of it, if not all of it. So I recommend watch this video. And if you have time, watch some of his other videos too, because they're great. I sometimes assign them as like extra credit in my math classes. So yeah, check out 3 Blue 1 Brown, and this video happens to be relevant to our particular topic. Okay, back to math. So here is another example that I want to do, which just to show you another type of problem that we can solve using inverse trig, or this is an expression we can simplify. And this is also something that comes up in calculus. And yet again, I can't tell you how many times I've seen calculus students not know how to do this because they forgot what I'm about to show you when they took pre-calculus. So let's simplify tan of cos inverse of x over 2. And we're going to do, the technique that we're going to do is draw a picture. I always recommend drawing a picture. So let's draw a picture of a right triangle that satisfies the information that is given to us. Now, cos inverse is an angle. Remember, inverse trig functions always spit out angles. So let's call this angle theta, okay? We don't know what it is, but let's call it theta. It's some angle, and let's draw a triangle that has that angle in it. So how about let's make this angle theta. Now, I don't know that much about theta, but I know that its cosine is x over 2. So that's the adjacent over the hypotenuse. And, well, let's just choose the lengths of our triangles such that the adjacent over the hypotenuse is x over 2. So let x be the adjacent and 2 be the hypotenuse. Let x be the adjacent and 2 be the hypotenuse. You see what I did there? I just assigned those lengths to those sides, and now I can use the Pythagorean theorem to figure out the opposite side. So, in other words, sorry, I'm getting like a phone call. What the heck? Ah. Man, I get phone calls and it starts like ringing on my computer. I need to figure out how to turn that off. It's really annoying. I don't know why it does that. I couldn't even see a way to like hang up on the phone call. All right. Sorry about that. Who calls it this hour? All right, whatever. That's what I was saying. So let's do the Pythagorean theorem on this triangle. Now we would like to figure out what this side is. But whatever it is, maybe I'll just call it, how about b for the moment. So x squared plus b squared is equal to 2 squared, i.e. X squared plus b squared is equal to 4. So b squared is 4 minus x squared. So b is the square root of that. And everything's positive here in this triangle. So we don't have to worry about a plus or minus. So we find that b is the square root of 4 minus x squared. So let's put that as square root 4 minus x squared on our diagram, on our picture. And now you can evaluate like what the other trig functions of theta are. Apparently, now tan of theta, which is opposite over adjacent, will be square root 4 minus x squared over x. Cool. And that's the answer. We simplified this expression. And like I said, you will definitely have to use this trick in calculus. So if I end up being your professor for 10B in the winter, don't let me catch you asking how to do this one, because I showed you and I told you you're gonna have to redo this one. well, I don't know, hopefully you remember. I mean, you kind of have to do stuff a few times before it sticks in your brain. You might forget, but hopefully it's easier to relearn the second time or the third time. Repetition makes perfect. Okay, anyway, that finishes up this section. Now, the next section I'm not going to finish today, definitely, but I will just do one quick problem to show you an application of solving trig equations, which is section 6.4. There's nothing really new in section 6.4. It's just applying what we've already learned. So let's just finish off by doing this example, where you've got a plane that's flying to a destination that's 200 miles north and 500 miles east of its location. So you want to fly, let's say that plane is right there at the origin. So if we use the typical never eat shredded wheat setup, we're trying to fly in that direction. Using inverse trig, we can figure out what our bearing should be or what our angle is. So how about if we let theta be the angle we make relative to the east direction? Apparently, let's see, if I draw this triangle, we've got sides of 200 and 500. So we can immediately read off that the tangent of theta is 2/5. So theta must be the tan inverse of 2/5. And there, that we figured out our bearing. Here, let me even plug that in to a calculator and see what that is. Tan inverse of 2/5 is 21.8 degrees. So 21.8 degrees. And now we know which direction to fly our plane. So you can see, like, this is really useful. And that's all I have time for